Hello friends, today we will understand Thevenin's theorem and Norton's theorem because in the gate problems most of the questions are based on this topic. So it is very important to start with this topic. To start with Thevenin's theorem first. Let us understand what Thevenin's theorem really means. You have to assume a complex electrical network. On those complex electrical network, you have to consider any two random points on it. With respect to these 2 points, rest of the circuit can be simplified into a very simple circuit having only one voltage source and having only one impedance which are connected in series with each other. The resulting circuit is called as an equivalent circuit. Since it is stated by scientist Thevenin, therefore it is called as Thevenin's equivalent circuit. I'll practically demonstrate you how does it happen. Let us assume some random circuit. It may consist of dependent sources or independent sources also. Assuming load resistor RL here. Therefore, considering 2 points, let's say across RL, again it is not necessary that A and B points has to be around RL. A and B points can be taken anywhere in a complete circuit. So for understanding purpose, I'm taking A and B across RL. As I said, Thevenin theorem means with respect to 2 points A and B, as you see on the screen, rest of the circuit can be simplified into a simple network. Except RL, rest of the circuit with respect to these 2 points which is A and B, this whole circuit can be simplified into a very simple network having only one voltage source, having this polarity, having only one impedance which is connected in series with a given voltage source. And these 2 points are there, that is A and B. The voltage source that we have obtained after few procedures is called as VTH. Now what VTH stands for? Thevenin's voltage. And the impedance which is connected with this VTH is called as ZTH. And what ZTH stands for? Thevenin's impedance. And the whole circuit, that is VTH and ZTH, along with these 2 points A and B, is called as Thevenin's equivalent circuit. So as I said, Thevenin's theorem states that with respect to any 2 points on a given complex electrical network, the whole circuit with respect to that A and B point can be simplified into a circuit having only one equivalent voltage source and having only one equivalent impedance which is ZTH and VTH respectively. And the resulting circuit is called as Thevenin's equivalent circuit. So this circuit is called as Thevenin's equivalent circuit. So whenever I say TEC, means it is Thevenin's equivalent circuit. So with this, let us try to understand Norton's theorem now. Again, let us consider some complex electrical network. Let me consider this value as RL. So I'll consider 2 points as we have done in Thevenin's theorem. I'm assuming same 2 points as A and B across RL. Now, contrast to Thevenin's theorem, Norton's theorem states that like with respect to any 2 points on a given circuit, the rest of the circuit is expressed as a simple circuit having only one current source and having only one impedance which are connected to each other. So as you can see, except RL, rest of the circuit with respect to A and B point can be simplified into a single current source and single impedance which are connected in parallel with each other, and again these 2 points are A and B. The resultant current source is denoted as IN, stands for Norton's current, and the resultant impedance is called as Zn, stands for Norton's impedance. So again, Norton's theorem also simplifying the network, Thevenin's theorem also simplifying the network. The only difference is Thevenin theorem gives you equivalent circuit in a way where you have only one voltage source and one impedance connected in series with it, whereas Norton's theorem helps you to simplify the circuit but in a way where you have only one current source and having only one impedance which are connected in parallel with each other. So the resultant circuit is called as Norton's equivalent circuit. So I'll say this is Norton's equivalent circuit. So whenever I'll say NEC, it means Norton's equivalent circuit. So as we have seen from these two theorems which are helping you to reduce the size of network to the simplified network, it means there will be definitely some relation between Thevenin's equivalent circuit and Norton's equivalent circuit. Now we are going to see what is the relation between Thevenin's and Norton's equivalent circuit. So it's a relation between TEC and NEC. If you remember, the Thevenin's equivalent circuit that we had is plus minus VTH, and to series to it there is ZTH with respect to 2 points A and B, whereas the Norton's equivalent circuit where we had only one current source having magnitude as IN, whereas we had one impedance which is connected in series with this current source called as Zn. Again, these 2 points are A and B. Needless to tell you, the first circuit is Thevenin's equivalent circuit and the second circuit is Norton's equivalent circuit. We are here to understand now relation between TEC and NEC. Relation as in, suppose if TEC given to you, then you don't have to go through the complete procedure to find NEC. From TEC only you can convert it into equivalent NEC. Or if the NEC for a particular network is given to you, you can come back to TEC also. So we are actually going to see how to convert Thevenin's equivalent circuit to Norton's equivalent circuit and vice versa. So assume that the Thevenin's equivalent circuit is given to us. So what is given is, let's say, TEC, and what is required is NEC. So if TEC given, it means two components must be given, that is VTH and ZTH. So TEC is given means VTH and ZTH are already given. And what is required to have NEC? Again, two values, that is IN and Zn. So what is required is IN and Zn. So the first relation is, whatever the value that you get is ZTH, the same value is Zn. So Zn is always simply ZTH. Whereas now see, Zn is already known to you, question mark is IN. But we shouldn't forget two values are given to us, that is VTH is given to us and ZTH is given to us. Suppose VTH upon ZTH, if we do that according to the Ohm's law, is going to give me some current. That is, by Ohm's law we know that current is equal to V by Z. Again check what is given to us, VTH and ZTH. Suppose I replace this V with VTH, and if I replace this Z with ZTH, the resultant current will be nothing but IN, that is Norton's current. It means ZTH is same as Zn and VTH upon ZTH will give me IN. This is how we can convert TEC to NEC. Similarly, we can also convert NEC to TEC also. So now we will see what if NEC is given to you and you have to get TEC, that is Thevenin's equivalent circuit. So this time let's say NEC circuit is given to us. We have to transform that into TEC, that is Thevenin's equivalent circuit. It means if NEC is given, so IN and ZN are given, and what are required? Required components are VTH and ZTH. So again, we know the relation that Zn and Zth are always equal. So in case if this is given and this is required, I can straight away get Zth by relation Zth equal to Zn. Zth is straight away equal to Zn. Whereas now Zth we have obtained, the question mark is on VTH. Now IN and Zn is given. VTH, or in general by Ohm's law, I can say that V is equal to I times Z. Suppose if I replace this I with IN and if I replace Z with Zn, then product of IN and Zn naturally gives me voltage, but this time voltage will be VTH. So this is how we get values of VTH and ZTH if IN and Zn are given to us. So I'll repeat this relation between TEC and NEC. Let's say TEC is given, NEC is required. TEC is given means VTH, ZTH is given. What is required is IN and Zn. So Zn is directly ZTH and IN is VTH upon ZTH. Whereas suppose if I have to convert NEC to TEC, that is Norton's equivalent circuit to Thevenin's equivalent circuit, then Norton's equivalent circuit is given as in IN and Zn is given. What is required? VTH and ZTH. So ZTH is directly equal to Zn, whereas VTH equal to IN times Zn. So I'm sure now you have understood what is Thevenin's theorem, what is Norton's theorem. Thevenin's theorem as well as Norton's theorem helps you to reduce the circuit into simplified network. Thevenin's theorem gives you VTH, ZTH, whereas Norton's theorem gives you IN and Zn. If this scenario is clear, we should understand the procedure to calculate Thevenin's equivalent circuit and Norton's equivalent circuit for a given complex network. So in the next slide, we will try to understand the procedure to get TEC. So let us understand procedure to get Thevenin's equivalent circuit. So we knew that a complex electrical circuit would be given to us where we will be having 2 points, that is A and B. So step number 1 is to open these 2 points. So step number 1 is to open 2 points A and B. Once we do that, we have to calculate voltage between A and B. That voltage is called as VTH. Step number 2. What we do is we short circuit these 2 points, that is A and B. Once A and B are short circuited, you have to find current flowing from terminal A to B. I repeat, you have to find the current flowing from terminal A to terminal B. That current is referred to as ISC. Then in the step 3, once VTH and ISC are obtained, you calculate ZTH, and ZTH is nothing but VTH upon ISC. So what we have done while calculating Thevenin's equivalent circuit, step number 1. In a complex electrical network, assume 2 points A and B. Open circuit these 2 points and find the voltage between A with respect to B. That is, A is plus with respect to B. So A will be plus, B will be minus. That voltage is called as Thevenin's equivalent voltage, that is VTH. After that, short circuit these 2 points, that is A and B. Find the current flowing from terminal A to terminal B. That is called as short circuit current, ISC. And in the last step, get ZTH by taking ratio of VTH and ISC. Similarly, we should see the procedure to get NEC, that is Norton's equivalent circuit. Let me tell you, Thevenin's equivalent circuit and Norton's equivalent circuit are actually same. That's the reason why we have seen there is some relation between Thevenin's equivalent circuit and Norton's equivalent circuit. So the procedure for calculating NEC will not be different. So within the same, I will tell you how to get Norton's equivalent circuit, that is NEC. Now, when we get NEC, again, step number 1 is same. That is, we open circuit 2 points A and B and we find voltage between A and B. That is what we call as VTH. So, while calculating NEC also, you get this VTH. This VTH is also called as VOC, and VOC stands for open circuit voltage. So, step number 1 is to get open circuit voltage between A and B. Step number 2, you short circuited 2 points A and B and found out the current flowing from terminal A to terminal B called as short circuit current. Let me tell you, the same short circuit current is called as Norton's current, IN. So this is IN itself. Whereas you get ZTH by having ratio of VTH upon ISC, but we have already seen Thevenin's equivalent circuit and Norton's equivalent circuit. When we were relating, I made you understand that Zn and ZTH are always same. So whatever you get ZTH here, the same value will belong with Zn. So this is how we can get TEC and NEC. You'll understand it in a better way once we understand the problem. Once we start solving the problems based on this. So that time, once we start applying these steps, then you will understand it in a better way. So I'm sure now you have understood what is Thevenin's theorem, what is Norton's theorem, what is Thevenin's equivalent circuit, that is TEC, what is Norton's equivalent circuit, that is NEC, the procedure to get TEC to NEC or NEC to TEC. Also, you have understood the procedure to get Thevenin's equivalent circuit and Norton's equivalent circuit from the given complex electrical network. Thank you so much for watching the video. Stay tuned to Ekeeda. Subscribe to Ekeeda.